of the constraint programming domain and mathematical programming domain. It is actually a relatively simple program, so it doesn't have some very big computational complexity. And why I'm mentioning mixed integer programming? Well, it is because the solution that we provided for this topic is turning this quadratic program, which is pretty simple, into a mixed integer program with some quadratic constraints due to the fact that we also introduced the equal opportunity constraint that I will mention in the next slides. And this is NP complete, so we don't expect our model to give us some feasible results in a very big amount of time or with a very big size of our data set, or I should say training sample. In order to express our idea, I should mention that we chose a certain branch of fairness, which is equal opportunity, which tells us that some positive outcome should be independent of the protected class and conditional only to the true label for it being positive. So we want to have true positive rates equal among both groups. And we will see in the next slides that this condition, as a mathematical formulation, we will add it into our SVM optimization problem. And for this, I want to show you briefly how the SVM looks. I think you are all familiar with it. It tries to minimize the hyperplane coordinates and also the error vector, which is the zeta. And this is all subject to having those constraints, which tell us that we should have a big accuracy, or we should classify correctly the points. And it is so a simple optimization problem. And we added some variables and some constraints in order to express our idea in a programming point of view. So we added a label which is telling us whether a point is extracted or not from our data set in order to tackle only the remaining points and to manipulate them in our equal opportunity constraint. And we also added some labels and variables that are expressing the sensible categories in our data set. We also need some non-continuous functions, which is, for example, the sign function or the indicator function, in order to express the fact that some individual is classified on the positive part of the space or in the negative. And so for this, what we see here shouldn't be so scary. It's just the normal optimization problem, which in which we added some constraints, and also a term in the objective function, which is the extraction label alpha y. And so briefly, we want to minimize the number of individuals which we extract from our data set. And for those who are remaining, we put them in that condition. We constrain them in order to achieve equal opportunity. Actually,
Elisabeta, just to be sure we are on the same page on this slide, the red part, the objective of the red part is to make sure that you are not removing too many things to constrain the number of example you extract, and the other part is to ensure that the one that remains are actually going toward the fairness you're looking for. Yes?
Yes,
Okay,
exactly.
thanks. Just
yes, and here we wanted to express the sign function for our position in the space, the fact that we want to situate ourselves on the positive class or not, and this is done by the indicator function. When we are positioning ourselves in the positive class, the indicator function is 1, so the constraint is going to just look to the others variables in order to satisfy all the constraint. And the problem with this is that from a computational point of view or programming point of view, we cannot solve this because it is non-convex and neither continuous. So we added another step, which is done by using the big M method, which is a method in mathematical programming, and which binarizes the constraint and which actually reformulates it and reconstructs it, and it is equivalent with what we have in the above constraint, which is non-continuous, and this is done by adding a surplus variable m, which is relatively large. It is larger than any other value, and it gives us the fact that we actually have quadratic constraints, because we also need to have a z vector in order to let's say complete our method, which is called the big M method. And actually at this step we were able to implement our problem in our code. And as an algorithm visualization, so first of all, we have input data, which has some random individuals, which has some sensible categories. We know this at the beginning, and we choose our parameters that I showed you earlier. And with those parameters, we construct our optimization problem. And on one hand, we want a very good accuracy. So the simple SVM, it is still in our solution, in our optimization problem, but also because we added those constraints and the alpha vector in our objective function, we also want to achieve equal opportunity. And so we arrive to have an hyperplane, so an SVM classifier, and we compute our fairness metrics. And in case, due to the size of the training sample or due to the values of our data, we may not have some better results than the initial problem. So we may rerun our program after we tune our parameters, and then we validate the model with those certain parameters and values. Here for experimental results, we considered 3 data sets that have been largely used to express this discrimination and this unfairness in machine learning classification. So one of them is the adult data set, which decides whether the annual income of a person may exceed $5,000 US, based on demographic characteristics. The adult dataset is the biggest when it comes to the number of records, and also it has a very high dimension. And the COMPASS dataset is used for judges in the USA in order to predict recidivism, which is actually predicting whether a criminal would reoffend or not in the future. For a German credit, this dataset tries to classify people as being good or bad credit risk. And we may see here that our sensible categories are gender and race. And on the next slide, we have some computational results. we can see that it gives us a better equal opportunity without losing some relevant difference in accuracy. For example, we can go from having equal opportunity 69.98 to 98.01. So it increases with more than 20%, almost 20%, and the accuracy, it just decreases with not even one value. And right, this is just 5% of our total results, as we have run hundreds of combinations of parameters and hyperparameters in order to validate our model and to analyze different sizes and different parameters. And so I will jump to the conclusion, which is the first one that, as I mentioned, we propose a novel quadratically constrained quadratic program formulation to build a support vector machine classifier, which includes fairness constraints. We also show an improvement in fairness without important loss in accuracy. We may see that sometimes this loss in accuracy doesn't even exist, even though this is rarely, but it may happen. Also, there is a small disadvantage, if I could say, in all this solution, because there is a trade-off between time and training sample size. And this is because, as I mentioned in the beginning, our mixed integer programming problem is NP complete, and it also have quadratic constraints, which construct a quadratic matrix. So we cannot expect to have all the time some feasible solution for each iteration that we are running for. And also, we have seen as an empiric observation that minimizing the extraction vector, which is alpha, determines that no individual is extracted from the dataset. Instead, there is affecting a bit the hyperplane. So as I mentioned, it gives us a smaller accuracy while trying to satisfy all these constraints and that minimization problem. And we think that we can also use our solution to other branches of fairness, for example, equal treatment, which is very similar to the equal opportunity constraint. Instead, it is representing that the true negative rates are equal among groups. And with this, I thank you for having your time to listen to me.
Thank you very much.